Okay, so again, we're going to be talking about dividing polynomials, so we need to think about what we know about division from elementary school. For example, if I'm doing 541 divided by 4, I set that up. 4 is my divisor, 541 is my dividend. So 4 goes into 5 one time, I multiply back. 1 times 4 is 4. I subtract, 5 minus 4 is 1. Bring everything else down. 4 goes into 14 3 times. 3 times 4 is 12. I subtract and I get 21. 4 goes into 21 5 times. 5 times 4 is 20. I subtract and I get a remainder of 1. So my answer is 135 is my quotient with a remainder of 1. So that's 1 over the divisor, which is 4. So 135 and 1/4. So now we can talk about the steps for polynomial long division, which is very similar to normal long division. So on the handout that you've been given, you have the steps for polynomial long division. So the first step is to see if you need any zero placeholders. So that's a new step because zero placeholders are already included in numbers. For example, a great question, what is a zero placeholder? If I have the number 1001, this 1 represents the thousandths place, so that's 1000. This is the hundredths place, the tenths place, and the ones place. So these are really like zero placeholders for the hundredths and the tenths. So we don't really call it that in that context, but if I'm talking about polynomials, x cubed plus 2x squared plus 5, what I would need to do is rewrite it with a zero placeholder because which term is missing? The x term. So it'd be x cubed plus 2x squared plus 0x plus 5. That's what it looks like to rewrite it with a zero placeholder. So that was a good question, Riley. Then we set up the polynomial long division, divide the leading terms, multiply the result by both terms of the divisor, and then subtract. And then repeat steps 3 through 5, just like we did here. We multiplied and subtracted 1 time, 2 times, and 3 times. So that's repeating steps 3 through 5 of this process. So let's say that our first example is to divide using long division, and we want to write our answer in the form q of x plus r over d of x, where q of x is a polynomial, r is an integer, and d of x is a linear polynomial. And we want to simplify any fractions. So step 1, we need to see if we are in need of any zero placeholders. So this goes from x squared to x and then to the constant term. So it doesn't skip anything, so there's no need for zero placeholders. So what I have to do then is go on to step 2, which is to set up the long division. So x minus 3 divided into x squared plus 3x plus 12. And you guys don't need to write this one, just watch this one. You can write the next one. So step 2 says I need to, for step 3, divide the leading terms. So in my thought cloud, I'm going to think about, okay, what is x squared divided by x? Right, so that's x. So x goes right here. Then I go to step 4. Multiply the result by both terms of the divisor. So I have to distribute x times both terms of the divisor, which is x minus 3. So when I do x times x minus 3, I get x squared minus 3x. So that's what goes right here, x squared minus 3x. Then I'm subtracting this entire thing. So remember, when you're subtracting, you have to distribute the subtraction sign. So that's why it says change, change, and then add down. Because subtracting is really like subtracting this and adding this. So change, change, add down. These cancel out, and they always should. 3x plus 3x gives me 6x, and I bring down the 12. Now I repeat steps 3 through 5. So I need to figure out what is 6x divided by x. And that is 6. So I get x plus 6, and now I multiply back 6 times x, 6x. 6 times negative 3 is negative 18. I'm subtracting the entire thing, so change, change, add down. These cancel out, and my remainder is 30. So if you notice in the example that we just did, the remainder of 1 was put over the divisor of 4. So when we're doing this problem, the final answer is going to be x plus 6 plus 30 over the divisor. And what's the divisor? X minus 3. So your final answer is x plus 6 plus 30 over x minus 3. Any questions on that example? Yeah. Okay, excellent question. Why do we divide just by x instead of x minus 3? It's for the... I'm trying to think of an example that would work with just basic numbers. Well, let me pause the video for this because I want to explore that question. Division. All right, so I would write this one right below, this example right below the steps for long division. So again, step 1 is to see if we need any 0 placeholders. We start with our x squared, then we go to x, then we go to 6. So there's no need for 0 placeholders. So we just set it up. So 2x minus 3 divided into 4x squared minus 2x plus 6. So step 3 now, step 1 is done, no 0 placeholders. Step 2, we set it up. Step 3, we divide the lead coefficients, or the leading terms. So I need to do 4x squared divided by 2x, which is 2x. Now I multiply that back by both terms, so I get 4x squared minus 6x. I'm subtracting that entire thing, so change, change, add down. These cancel out as they always should, and you get 4x plus 6. So then we repeat that process. So divide the lead terms, 4x divided by 2x, which is just 2. So I get 2x plus 2, and now I multiply that by both terms, so I get 4x minus 6. So subtract, which means change, change, add down, and I get a remainder of 12 in this instance. So it'd be 2x plus 2 plus 12 over 2x minus 3. And now we have a fire drill. Absolutely, you can hear it. All right, so this is the last one that I asked for you guys to write down, and this one's useful because step 1 actually requires us to do something, because we need a 0 placeholder. So notice we skipped the x cubed term, so this should actually be written as 4x to the 4th. So when I set it up, 2x minus 1 divided into 4x to the 4th, I need to add the 0 placeholder for 0x cubed. Then I can do minus 5x squared plus 2x plus 4. So can everyone see how the 0 placeholder factored in there? Yes. All right, so that's important. Otherwise, I will ignore kind of a whole column. Just like if you're doing like 100 plus 20, let's actually say 101 plus 25. If you don't include the 0 placeholder, you end up actually doing 11 plus 25. Same thing here. If we don't include the 0 placeholder, we'll end up skipping the cube term, and it'll mess everything else up. So divide the lead terms, 4x to the 4th divided by 2x gives us 2x to the 3rd power. So that's the first term of my quotient, 2x to the 3rd power. Now I multiply that back by both, and I get 4x to the fourth minus 2x cubed. I'm subtracting that entire thing, so change, change, add down. Those cancel out as they should. Get 2x cubed. And we just bring everything else down. Minus 5x squared plus 2x plus 4. Now I divide the lead terms again. 2x cubed divided by 2x, which gives me just x squared. So this will be plus x squared. Now we multiply that back by both. Oop, I don't mean to cut through that, but that's okay. So we get 2x cubed, and then x squared times negative 1 minus x squared. So change, change, add down. Now we have negative 4x squared plus 2x plus 4. And this one's it's a hefty one. So now I need to do 4x squared divided by 2x, specifically negative 4x squared. So let me do it over here. Negative 4x squared divided by 2x is negative 2x. So I have minus 2x here. And then I need to multiply that back by both terms of the original polynomial. So I get negative 4x squared and then plus 2x. So now change, change, add down, both get eliminated. So I'm left with just 4, which means that 4 in this instance is actually my remainder. Because I can't do 4 divided by 2x without getting, we always want to do this part divided by this. So 4 divided by 2x, I'm going to get an x in the denominator, which we don't want. So 4 is just our remainder. So our final answer would be 2x cubed plus x squared minus 2x plus 4 over 2x minus 1. Let me pause the video to actually check that answer. Yes. Thanks for watching the polynomial long division video. Here's one to try on your own, and we'll post the answer in just a second. So there you go. There's your solution, courtesy of Lex Verani. 4x squared plus 10x plus 25 with a remainder of 0. Have a great day. This video brought to you courtesy of Duke Productions.